So okay. So this next assumption is flow through the back insulation is one dimensional. So the heat transfer is in one particular direction. That is the major meaning of this sentence. So because there will be some heat transfer in this direction also, but the major heat transfer will be in one particular in this direction, right, perpendicular to the plate, right. Next is temperature gradients around the tubes are negligible. Around these pipes in which the working fluid is moving, the temperature gradients around these tubes is assumed negligible. It means the temperature of this whole tube will be one particular temperature, or one uniform temperature will be maintained around these tubes. So the gradients around these tubes are negligible. Next, properties of the collector materials are independent of temperature. Properties such as, for example, the transmittance, absorptance, emittance of these different materials like glass covers and plate, and thermal conductivity of insulation, or thermal conductivity of this metal absorber plate. So all these properties, thermodynamic properties, which are a function of temperature, so those are assumed to be constant. They are independent of temperature. So for example, the absorptance of this coating is 0.98, and this absorptance is not a fixed value. It is also a function of temperature also. But that dependence on temperature is not very strong, so that's why we can neglect the dependence on temperature of all these thermodynamic properties. Next is that heat flow through the cover, through this glass cover, is one dimensional. That is another assumption, that just like insulation, for the case of insulation, we said that the heat transfer is one dimensional. Similarly, heat transfer through this glass covers, because heat will be transferred from this high temperature to low temperature ambient, and this heat transfer in this direction also has a glass cover in between, and there could be one, and there could be two or three glass covers. So the heat transfer through these glass covers, which will be by conduction, so that is also assumed to be one dimensional. Next, temperature drop through the cover is negligible. It means the conductive resistance of these glass covers are assumed negligible. So we would be saying that the temperature on this edge is equal to the temperature on this edge. So because normally the thickness of these glass covers are so small that we can assume that the temperature drop across this thickness of this glass cover is negligible. Although thermal conductivity of glass covers is also very small, but because thickness is so small, so from the Fourier's law of heat conduction, the effect of thickness is quite significant in this case. So that's why the temperature difference will be very small or negligibly small between this edge and in the next edge. So the same is for the second cover. So the temperature drop through the cover is negligible. Next assumption is covers are opaque to infrared radiation. It means these glass covers will not allow the transmitted radiation to transmitted which radiation? This emitted radiation from the absorber plate, those radiation will not be transmitted through this glass cover, right? Those will be blocked by the glass cover. So that is the next assumption. Then same ambient temperature exists at the front, that is the front side of the solar collector, and that is the back side of the solar collector. So the ambient temperature is assumed to be same on both sides of this solar collector. Then the effect of dust on these glass covers are also considered negligible, because dust will affect the transmittance of the glass cover. So, but here, for the sake of simplicity, we are assuming that their effect is also negligible. Next assumption is there is no shading of the absorber plate. So the shading effects from the surrounding surfaces is also assumed negligible. So these are the number of assumptions which we have just studied. So our numerical model will be based on all these assumptions. So you will see, even on the basis of all these assumptions, the numerical model will not be that simple. It is quite complex. Right. So now next we shall study the basic flat plate energy equation. So now we shall develop the thermodynamic equation on the flat plate solar collector, which we can solve to find out the heat gain of the solar collector fluid which is flowing through these tubes of that solar collector. Right. So here the thermal performance of a solar collector can be calculated from the first law energy balance. First law energy balance simply means the energy balance which is based on the first law of thermodynamics. So, and we know the first law of thermodynamics simply says that the all of the energy which is entering into a system must be equal to the energy which is leaving the system if there is no storage. So if we see here, the total energy gain of this solar collector Qu will be is equal to energy absorbed by the solar collector minus the heat energy which is lost to these surroundings. For example, let me draw a flat plate absorber plate. So that is the absorber plate, and the radiation which is absorbed by this plate is S, and then there will be certain losses from the top and also from the bottom. So for example, that is Q loss, QL or Q loss. So this is the input energy and that is the output energy or the loss. So this minus this is the energy which stores here or which is transferred to the working fluid flowing through these pipes. So if this absorber plate is our system, this is system boundary. So across this system, what is happening, this energy is entering, which is S, this energy which is leaving in the form of loss, and there is another energy which is leaving in the form of heat gain of the fluid, that Q. We may say it is QU, useful energy, which is transferred to these tubes in which a working fluid is flowing. So the energy entering S must be equal to energy leaving in the form of loss and in the form of useful energy. So that is actually written here. The total useful energy QU is equal to S minus Q loss, heat loss to the surroundings. So the energy absorbed by the solar collector, which we have represented by this symbol S, is equal to the difference between the incident solar radiation and the optical losses. So we have already discussed what is this S. This S is actually incident radiation, which we represented by G for instantaneous radiation, right? And into the optical losses means this tau alpha product. This S, the absorbed radiation per unit area of this absorber plate, is equal to the difference between the incident solar radiation and the optical losses, and which is defined by this equation which we solved in chapter 2. And this was derived in chapter 2. Starting from chapter 1 till chapter 2, this was the final equation which represents this absorbed radiation on the solar collector. So this absorbed radiation equation is actually not only valid for flat plate, but the same is also valid for other types of solar collectors, with little difference as how you calculate this tau alpha for this flat surfaces and for curved surfaces in case of evacuated or concentrated type of solar collectors. But the overall concept is exactly same for any type of solar collector. So that is the absorbed radiation S, which is actually in general you may say it is G into tau alpha. where G could be I if it is hourly radiation. The same G could be H if it is daily radiation. Okay, so similarly the thermal energy which is lost, because now we need to find out this loss, right? We have already estimated or calculated this energy absorbed, which is this one, this equation. Now we will focus on this part, which represents the heat loss back to the surroundings. So the energy which is lost is by, of course, conduction, convection, and infrared radiation from this plate back to the ambient. And this loss can be represented, this QL can be represented as a product of overall heat transfer coefficient from heat transfer basics. If you remember, that is overall heat transfer coefficient into temperature difference, which is Tp minus Ta. We are writing everything so far for per unit area, right? The units of U, watts per meter square per Kelvin into Kelvin. So this QL is also in watts per meter square. This S is also in watts per meter square. Right, so this QL, so in heat transfer normally we use these smaller symbols for per unit area. So that is the heat loss QL from this absorber back to the ambient is given by UL into TP. TP here is the mean plate temperature. Right? Here TPM represents the plate temperature, and this plate temperature will not be a constant. In reality, this temperature would be varying over the whole surface, but here for the sake of simplicity we are assuming it to be at one uniform temperature, that is represented by TPM minus TA, the ambient temperature. So here is the representation of this energy balance also, that is the available radiation on a tilted surface GT. Some portion is reflected, some portion is transmitted, and that is the energy which is finally absorbed on the surface, and some is again reflected. And on the basis of all these phenomena which are occurring here, this equation was developed. Now there will be losses from this absorber plate back to the ambient, and that is given by UL into TPM minus TA. So that represents the loss part back to the ambient for per unit square meter of this from per unit square meter of this absorber plate. Okay, so now we can write these equations here in equation 4.1. So that is QU. Now energy absorbed is given by S, this term S, minus what is this? This is the loss which is given by U into TPM minus TA, this part. And so both of these terms in equation 4.2 and 4.3 are for a unit area. And what is the area from which this loss is occurring, or the area on which this energy is absorbed, is actually the absorber plate area. That is actually a absorber or collector area, this absorber plate area, right? So we can write this equation 4.1 in terms of mathematical symbols. So that is the QU, useful energy gain, is equal to absorbed minus loss, and this absorbed and loss, heat loss, is occurring from the same area AC. So AC is common to both of these terms, right? So now this equation is the basic energy balance of flat plate thermal solar collector, and so far we are discussing liquid flat plate solar collector. Okay, so now to solve this equation, there are still some unknowns which needs to be calculated. We know how to calculate S already, but now this term is still to be calculated properly. And also this temperature, this TPM, normally ambient temperature, we know at a particular instant we can calculate, or we can actually measure this ambient temperature where this solar collector is placed. But now we need to determine this TPM, this temperature, absorber plate temperature, TP. Subscript M simply means that represents the mean plate temperature. Okay. So this TPM is unknown, and that is not easy to calculate because it is a function of many things depending upon the amount of radiation which is available, total G. Right, so this TPM is a function of the type of solar collector which we are using, flat plate, evacuated, or any other type of solar collector. And even in the flat plate solar collector, there are many variations how the plates are attached, right? How the tubes are attached. Tubes are attached on the top or on the bottom of this surface, and the amount of the type of fluid which is flowing through these tubes, and also the flow rate at which this fluid is flowing through these tubes, that will also affect ultimately this TP, the plate mean temperature. So plate temperature is actually affected by a number of parameters. One is available radiation, then the radiation properties of this glazing and absorber materials, what is tau, what is alpha, and how this tau and alpha are changing with the angle. What is this angle? Incidence angle, because we know this tau and theta are a function of tau and alpha and emittance. Those are actually a function of incidence angle. So as this incidence angle is changing, the absorbed radiation S will be changing. As the absorbed radiation is changing, the amount which is lost and the which is transferred to this fluid will be changing. So this TP is not that simple to calculate because it is dependent upon many parameters: the type of collector design, the available or absorbed radiation, right, and also the condition of this fluid which is flowing through these tubes, at what flow rate and at what temperature it is entering into this solar collector. So all these parameters are actually affecting this TP, and this TP or TPM is necessary to calculate the useful gain of the solar collector. And also in the calculation of this U, which we will discuss next, the overall heat transfer coefficient, we cannot calculate this overall heat transfer coefficient without the knowledge of this plate temperature and glass cover temperatures. Right. So these two unknowns are not that easy to calculate, so this is something which we will now learn, how to calculate or estimate these two unknown, UL and TPM, and both are dependent on each other, this overall heat transfer coefficient and overall heat loss coefficient, and the mean plate temperature. So that is explained here. The problem with this equation 4.4 is that the mean absorber plate temperature is difficult to calculate or measure because it is a function of the collector design and the incident radiation G and the entering fluid conditions. So this equation will be reformulated, this equation 4.4, so that the useful energy gain can be expressed in terms of fluid temperature, because the fluid temperature which is flowing through these tubes will be at a temperature, for example, TF, right? But this equation 4.4 does not is not on the basis of TF, it is on the basis of mean plate temperature. So we can reformulate this equation 4.4 in such a way that TF will appear here instead of TPM, but there will be certain changes in this equation, because sometimes actually we are interested to know the fluid temperature at the exit of this solar collector. For example, this is our solar collector. Fluid is entering and leaving. It is entering temperature TFI and leaving at a higher temperature TFO. So for a non-TFI, we are interested to know what is TFO. If this fluid is moving with mass flow rate m right? And its initial temperature is TFI. Now we are interested to know what is TF4. When this solar collector is exposed to absorbed radiation of S and there are losses in the form of heat back to the ambient, which is given by Q, which is U into delta T. So, but this equation is not on the basis of fluid temperature, and also the effect of mass flow rate is not clearly mentioned in this equation 4.4. But this mass flow rate and this fluid temperature, inlet fluid temperature of the fluid will affect this TPM. So that's why we shall write this equation in other forms also, in terms of fluid temperature also. Now, from this analysis which we have done so far, we can define the efficiency of this solar thermal collector, because in any thermodynamic or thermal system, we are always interested to know the efficiency of that system, right? So efficiency is normally defined as eta, the symbol which is used to represent efficiency, and that is given by desired output, not just the output but the desired output. And what is the desired output of this solar collector? And that is QU, the useful heat gain. This TF4 minus TFI multiplied by m dot into Cp, right? If this fluid is only changing its temperature, then the heat gain of this fluid is given by m Cp into this change in temperature of the fluid, delta Tf. So that is actually QU, and this QU is actually equal to this QU. So the QU, which is calculated from this equation 4.4, must be equal to this QU, the heat gained by this fluid. So that is the useful output of that solar collector, that is QU. So the useful output is actually QU. And here you can see this equation is for one particular instant, because everything is for joules per second, because that is watts per meter square means joules per second meter square. Similarly here it's also watts per meter square per Kelvin. So again watts, so it means at one particular second. So if we want to find out this QU over a certain time period dt, from for example morning till evening, or for the whole day, for the whole week, or for the whole month, then we have to integrate this equation over this time period dt. So that is the useful or desired output. What is the required input? The input energy for this solar collector is this one, the incident radiation, that is G, which we have represented by G on this tilted surface. We know the reason behind why it should be tilted. So right, so normally it is tilted, so that's why GT. This is the input energy, and again the units are watts per meter square, so we have to multiply with the area over which this energy is being intercepted and finally absorbed, right, after optical losses. So GT, available radiation, multiplied by this area of the solar collector, which is AC, we have represented. And again, if the units are watts per meter square, so we need, for long-term analysis, we need to integrate, just like in the numerator. So that is the input energy, right, on the same area. And from the same area, that is the useful heat gain of the fluid. So that's how we can define the efficiency of any solar thermal collector. The input energy divided by the output, useful output, divided by the required input. So that's how we can define the efficiency. So that is collector efficiency, where AC is constant area, so that's why it is written outside the integral. Okay. Now we have this equation 4.4. Now we shall solve this equation. First we shall solve this U, because we need to know what is the value of U. So now we shall learn how to calculate this overall heat loss coefficient. for a known plate temperature and for a known ambient temperature. For this temperature difference, how to calculate this U, the overall heat transfer coefficient. So that is the next step to calculate the U value, which is to be used in this basic energy balance of flat plate solar collector, which we have written here in the form of equation 4.4. So the next part is to find out the overall heat transfer coefficient U. So for that we need to understand this phenomena of heat loss. So this is our absorber, this is glass cover. So for example, this absorber is at a temperature of Tp, which is initially not known, so we shall assume this Tp. Then there is a glass cover whose temperature is Tg, which is also unknown, so we shall initially assume Tg. Then here is ambient temperature Ta on the top or on the front and on the back side of this glass cover, which is normally known to us. So in this equation, in the basic energy balance, we want to find out this U from every side, U from the top side, U from the bottom side, and U from the two sides. So that is U from the sides, U from the top side, and U from the bottom side. So that is the heat loss from the top, represented by UT, from the bottom represented by UB, and from the sides represented by US. Okay. And the summation of these three, UT plus US plus UB, is represented by UL, overall heat loss coefficient, which is shown here. Okay, so now this is Tp, so Tp will be the highest temperature. This temperature will be highest because this plate is absorbing maximum of the radiation, and this will be the lowest temperature, ambient temperature, and Tg temperature will be intermediate temperature between Ta and Tp, because it is absorbing very less amount of solar radiation. Maximum of it is transmitted, so that's why its temperature will be smaller than Tp. But its temperature will be higher than Ta because some of the energy is lost back from Tp to Tg, and there is air normally. There is air in this space between glass and plate, so that's why the heat loss from this plate to glass will be by convection or conduction through this air. That's why the glass will absorb, or some heat will be transferred from plate to glass by convection, right? So from this plate till glass there will be heat transfer by convection, because there is a gas at 1 atmospheric pressure. If it is not evacuated tube solar collector, if it is evacuated tube solar collector, so there will be no convection. And also there will be loss from this plate to this glass due to radiation. So for convection part, we represent it with Hc, convection, from plate to glass. And there will also be radiation heat transfer from plate to glass. So that is shown here. So that is Tp, this is Tg, and between Tp and Tg there are heat losses due to radiation and also due to convection, but here we have shown it in the form of resistance, thermal resistance. So this heat transfer HRPG or HCPG, if we divide it by 1 divided by HCPG, it becomes thermal resistance. Similarly, 1 divided by HRPG becomes thermal resistance. So here we have shown this heat transfers in terms of thermal resistance, right? So that is a procedure which is normally adopted in heat transfer analysis, which you would have studied in the undergraduate course of heat transfer. So these are the two heat transfer resistances, one in the form of radiation, second in the form of convection from plate to glass. Then from glass to ambient, there will again be heat transfers due to radiation and also due to convection from glass to ambient, from Tg to Ta, because Tg is greater than Ta, so there will be heat loss from the glass to the ambient. Again, there will be two modes in parallel. One is the radiation heat transfer mode, second is the convection heat transfer mode, from glass to ambient and from glass to ambient in the form of convection and radiation. So a summation of these two resistances can be represented as R. Total resistance, thermal resistance from G to A is equal to 1 over HCGA plus 1 over HRGA is RGA. And here, if you remember, there was one assumption that the heat transfer resistance of the glass through the within this glass slab having certain thickness is negligible. If this glass cover heat transfer through this glass cover is not negligible, then we have to account for the conduction heat transfer through this glass cover also. But that is assumed negligible. That's why we have written simple Tg. Otherwise, we have to include here one more heat transfer resistance, which is the conduction heat transfer resistance through this glass cover. So that is assumed negligible. Right. So that is the heat transfer network, heat transfer resistance network from plate to ambient, plate temperature till ambient temperatures. And that is represented by a heat transfer resistance from glass to ambient and heat transfer resistance from plate to glass, which consists of further consist of two parts. One is convection or conduction and second is radiation. Right, so this is all about the heat transfer from the top of the plate, right, which we have represented as UT, heat transfer from the top. Similarly, now we have to see what is the heat loss from the bottom of this collector. From the bottom, so what is beneath this absorber plate? We have insulation, a solid insulation. So there will be no convection. There will only be heat transfer from this plate to this bottom surface. Let's name this TB. Temperature of this bottom surface is TB. So from TP to TB, there is a heat transfer resistance only due to conduction. So that is given by delta X over K, or heat transfer in the form of resistance. Or in other words, the heat transfer from plate to this bottom, TP to TB, will be by K over delta X, but in the form of resistance, it will be delta X over K. Right. So if you are not clear with this term, if you're not familiar with this term, so I would ask you to please go through your thermal heat transfer basics again, so you will know what is actually meant by delta X over K. Everything is written here in for 1 square meter of absorber plate. So all of these terms, their units are watts per meter square per degree change in temperature, or the per degree change or the difference in temperature. Then from TB to ambient, again there will be two heat transfer resistances in the form of radiation from bottom to ambient and in the form of convection from bottom to ambient. So that completes the heat transfer resistance of our flat plate solar collector. So now we shall learn that how to determine all of these heat transfer coefficients. What are the appropriate equations which can be used to find out all these heat transfer coefficients, HR, HC from glass to ambient, similarly from plate to glass, and from plate to bottom, and from bottom to ambient. Right. So similarly for the bottom part, the heat transfer resistance is shown. Heat transfer resistance from plate to bottom, heat transfer resistance from bottom to ambient. So sum of all the heat transfer resistances are GA plus RPG plus RPB plus RPA is shown here as RL. Overall heat transfer resistance, because that is the energy which is absorbed by this plate. That's why its temperature is increased, and now there are losses from plate to ambient, which is given by this heat transfer resistance value. RL is equal to 1 over UL into area. What is this area? The whatever heat is being lost or absorbed is from that common area AC. So all of these coefficients are actually corresponding to the same area, which is the collector or absorber area. So, okay, I stop here. So we shall continue from this slide onwards in the next lecture.